Hey guys, my name is Trevor Sullivan and welcome back to my video channel. Thank you so much for joining me in another video where we're going to continue learning about the Rust programming language. Now, the topic for today's video is going to expand upon some of the core concepts that we've already covered in the existing Rust playlist. A couple of those concepts that we're going to be building on top of are things like generics, as well as traits and trait implementations for certain concrete types that we've declared in our Rust application. We're going to be talking about how traits work for dynamic dispatch in particular. Now, if you've ever felt constrained by the type system in Rust and you feel like you're duplicating a lot of code in order to implement certain behaviors for certain data types, then the concept of dynamic dispatch with traits will probably free your mind a little bit and hopefully give you some additional tools in the Rust language that will help you to write more robust and less duplicate code. Now, there's also another concept around traits known as supertraits, and that's a pretty simple concept. A super trait just basically allows you to group a series of traits together and define all of those different traits as a singular super trait so that you can manage that behavior of those different implementations of your types in a more consistent fashion. So we're going to be exploring all of these different concepts. Hopefully, by the end of this video, things will be broken down in a more easy to understand way for you so that hopefully you can use dynamic dispatch and traits more effectively in your applications. Now, keep in mind that dynamic dispatch is an alternative to using generics. There is a computational cost to using dynamic dispatch. So if you're looking to write code that's going to perform at runtime the absolute best, then you'll probably want to stick with generics. But if you're okay with taking a slight performance hit to your application, then using dynamic dispatch is a great way to write dynamic code. And it can also result in smaller binary sizes because the dispatch is being done at runtime rather than at compile time. So the compiler for Rust isn't necessarily having to duplicate the implementations of your generic functions. Now, there's a few different articles that we're going to be talking about when it comes to traits and using dynamic dispatch. So we're going to talk about those in just a moment. But first, I just wanted to invite you to subscribe to my YouTube channel. I'm an independent content creator, so any kind of support that you can lend to my channel would be extremely helpful as I continue to grow this community and produce training on various topics, such as the Rust programming language. Also, if this is your first time checking out my channel, keep in mind that I do have playlists available, so feel free to head out to the playlists tab where I have a Rust programming tutorial playlist, along with a number of other interesting playlists on technologies like LXD for virtualization on Linux. But right now we're up to 24 videos on the Rust programming tutorial series here, so I hope that you'll go back and watch some of these earlier videos if you need to brush up on some core concepts in the Rust programming language. Also, if you learn at least one thing new by the end of this video, please leave a thumbs up or like on this video, and also please leave a comment down below. Let me know what you thought of this particular video. Let me know what you think of the teaching style, if you like it, or if there's something else that you'd prefer. And also let me know what other kind of topics beyond just Rust that you'd like to see me explore on my video channel. So with that in mind, we're going to go ahead and jump into the concept of dynamically sized types. So as the documentation for the Rust reference here indicates, this is section 10.2 here in the Rust reference. This is going to talk a little bit about dynamically sized types. And when we start dealing with dynamically sized types, those have to be allocated on the heap because any values that are going to be stored on the stack need to be known at compile time. So we can't necessarily put things that are dynamically sized on the stack. They have to be heap allocated, and then we have to have a stack pointer to those dynamically sized values. So there's a couple of things that fall into that dynamically sized category, which is slices and trait objects. And as we know from the video where we talked about traits, traits are at a very fundamental level just a way for us to define common behavior across different data types that we've declared inside of our application. So if we have a dog and an antelope struct, then we can implement common functionality across those different animals, like eating food, or perhaps making some kind of noise, like a dog barking, an antelope bleating, Antelope would maybe eat vegetables like, plants that they find out in nature, whereas maybe a dog eats dog food and is a carnivore. It eats other types of meats, right? So the actual implementations of those two different animal types is different, but we can still share the common types of behaviors. Running is another type of common behavior that you might find across multiple types of animals. So when we actually define our concrete implementations of these data structures, we can simply tack on these trait implementations and make sure that the compiler knows that we want to define this common set of behavior across those different types. And when we make functions, we can actually use traits as input types using generics, and that's going to cause the Rust compiler to take a little bit more time at compile time to generate the function implementations for each of the types that is implementing that particular function, or that function references as a trait type. And then if we use dynamic dispatch, which is what we're talking about in this particular video, then in that case, things work a little bit differently. So what happens with the traits when it comes to dynamic dispatch is that traits will actually create something known as a virtual method table. So when you implement a trait and use dynamic dispatch, you're going to get two different things. You're going to get, number one, a pointer to the underlying data structure that implements the trait. And then the second thing that you're going to get is a pointer to this virtual method table. Actually, not a pointer to the virtual method table, but it actually creates the virtual method table itself. This is a lookup table that basically allows any references to that particular trait to look up dynamically the implementation of a particular function for a given type at runtime rather than at compile time. So that's where the extra computational overhead comes from when you are using dynamic dispatch instead of generics. So generics can cause slightly longer compile times and slightly larger binary sizes because there is some code duplication happening within the compiler itself, not in your Rust application, but inside the compiler, it's actually duplicating the code for generics for each concrete data type that implements a particular trait. But when we use this dynamic dispatch, it's basically just creates these pointers to the implementations of these functions, and then the lookup is done at runtime of your application. And by using dynamic dispatch, what this allows us to do is to do things like pass in a dynamic trait as part of our function input arguments, and that way we can actually declare a function that can operate over many different concrete implementations of a particular trait. So rather than passing in a generic type, this time we're just specifying a dynamic pointer to a particular trait instead. And then any type that implements that trait can be used as an input to that particular function. So if we have 10 or 20 different types of animals that all need to implement the eating function and the running function and the making noise function, whatever that animal noise happens to be, then we can use this dynamic dispatch capability to implement our code once, but have many different types that are actually being able to be passed in to this function call. So this helps us to deduplicate our code with a slight overhead cost. Now, there are some other articles that talk about dynamic dispatch. So in the Rust by example book here, we have another article that talks about returning traits with dynamic dispatch as well. So not only can we use dynamic dispatch as function input arguments, but we can actually have a function return a trait that points to a different type of data structure depending on what that function wants to return. So we could have a function that returns maybe an animal type, but depending on certain factors, maybe the time of day or the date or the year that it is, that function could actually return different types of concrete types. So we might have a sheep, a cow, or an antelope or a dog. And instead of returning the concrete implementation, the function is actually going to return a boxed pointer to the trait implementation. And again, that trait is going to have a pointer to the virtual lookup table for the method implementations. And it'll also have a pointer to the concrete structure that is being referenced by that particular trait. So we can use dynamic dispatch for input arguments to functions. We can also use them as return types for functions as well. And that gives us a lot of flexibility in how we write our Rust code. So with all of that in mind, we're also going to talk about super traits. Super traits are pretty simple. It basically just allows us to have a trait that implements multiple other traits. So if we have maybe an eating trait for an animal, a running trait for an animal, and we also have we have eating, running, and noise making, right? So we have three different traits that we want to do for common functionality across animals. But then what we can do is actually wrap up all three of those traits into a super trait so that we can start to work with just animals in general rather than having to reference the specific functionalities across the different traits like noise making or eating or running and things of that nature. So super traits kind of go hand in hand. You don't necessarily have to know super traits in order to use dynamic dispatch, but you start to see the value of working with super traits and how it allows you to pass around dynamic references to arbitrary data types rather than having to pass concrete data types themselves. All right, so there's one other article I wanted to point you to that talks about dynamically sized types, which is under the Rustnomicon book here. And this has an article called Exotically Sized Types. So you might want to check that out as well if you want to do additional reading on the dynamic dispatch concept. So with all that in mind, let's go ahead and actually take a look at how to implement dynamic dispatch inside of a code project. So I'm going to head over here to my editor, which is Microsoft Visual Studio Code. I have VS Code running on Windows 11, but I am remotely connected to an SSH server, a Linux server that has SSH installed on it. And it's basically just a virtual machine that's running on my LXD infrastructure. So this is a great way for me to just kind of spin up development virtual machines running Linux. And then I can do all of my Rust development on a high performance Linux virtual machine rather than developing locally on Windows. Of course, maybe I want to write a cross-platform application and I want to test it on Windows, but generally speaking, I like to do Rust or really any kind of development work on a headless Linux server. So what we're going to do is just create a new project here called test-din traits. And we'll go ahead and open up that folder. So we'll do Control-K, Control-O in VS Code, and then we'll open up that test-din traits project folder here. And everything that we do is going to be from scratch here. So I'm going to literally just spin up a new Rust application by running the cargo init command in my project directory, and that will scaffold out a basic project with a main.rs file. That's my entry point to my application. I've also got my cargo.toml file that has the metadata for my crate here. So I can rename this crate if I want to, give it a version number. I can declare any dependencies that I might have. In this case, we're not going to be using any third-party crates because this is all just core Rust functionality that we're going to be talking about. So what we're going to do is come over to my main.rs file here, and we're going to declare a separate module file. So we'll say pubmod, and then we'll call it trait test. And then we'll go ahead and create that file in our project here. So we'll call it traits test.rs, and then we'll just call into this module from our main function here so that we're not kind of gumming up our main.rs file with a bunch of code. All right, so what we're going to do in here is create a public function that'll serve as our entry point to testing out traits. So we'll go ahead and just call this test, or maybe run trait test. Doesn't really matter what you call it. I'm just trying to come up with some kind of logical name for my function here. And then what we're going to do is implement some concrete types here, some data structures. And these data structures don't even necessarily have to have any data fields declared on them. We simply need to declare different structures with names like dog, antelope, bear, whatever you want to call them. And then we're going to implement traits that actually define the common behavior across them. So we're not really going to be mutating the state of these structs, so we don't need any fields to mutate. So we'll do a struct dog, we'll do another struct antelope, and we'll do another struct of bear. Now, all three of these animals here, dogs bark, antelopes make a bleating sound, and bears make a roaring sound, right? So those are all different types of sounds that they make. Also, when it comes to eating, dogs might eat dog food, antelopes might eat natural plants that they find out in my yard, and bears eat other types of animals, right? They probably also eat some kind of nature too, but the idea here is that a bear can eat things that antelope probably don't eat, in addition to some plants as well, right? So we have different implementations for each of these types of animals. for noise making, for eating, as well as for running potentially, right? And perhaps other behaviors, like maybe they scratch themselves, maybe they, um, you know, there's all sorts of different functionality that could be different between these. So what we're going to do is define a trait down here for eating. So we'll say animal eating, and then we'll define another trait right down here for animal sounds. Okay, so we'll just call it animal sound. And then inside the trait, we can declare the methods or the common functionality that we want across these different concrete data structures. So what we'll do is start by declaring a function on animal eating called eat food. And because this is going to be an instance level method, we need to make sure that we pass in self, which is the reference to the current instance of whatever object that is. So for animal sound down here, we'll do make sound and pass in a pointer to self there as well. And then we need to go ahead and implement these traits for each of these animals that we have here, right? And so this is what's going to allow us to have generic functionality across all these different animals. So we'll say impl animal eating for dog, and we'll just say fn eat food. VS Code with Rust Analyzer auto completes that method signature because it knows what that method signature is going to look like from the method declaration on the trait itself. So we'll just say print line. Whoops, let's do print line here and say dog is eating dog food. All right. And then we'll also implement animal eating for the other types here. So we'll say for the antelope. And so we'll do an implementation of eat food and say antelope is eating natural desert plants. And then we'll do the same thing for the bear. So we need to implement animal eating trait for the bear. So we'll say bear is eating some other animal. All right. So now we have implementations for animal eating trait for all of these three data structures that we've declared. So now we want to go ahead and do the same thing for animal sound. So we'll do impl animal sound for dog, and we'll go ahead and implement make sound. And then we'll say print line dog is barking. Then we'll do the same thing for our antelope. So we'll change the type here to antelope, and we'll say antelope is bleeding. And then finally, we'll go ahead and duplicate this one more time for the bear type, and we'll say bear is roaring. And if you hear a bear roar, you probably want to head the other direction or pull out your bear spray. All right, so now we have implementations for two different traits, animal eating and animal sound, for all three of our different data structures. So that gives us a total of 6 implementation blocks down here for the two different traits across 3 different animal types, right? Now, let's say that we want to construct one of these animals and implement a function that operates on any of these animals, right? So let's do a dog constructor here. So we'll say let dog equal dog. We'll say dog 0, 1, just in case we want to create additional dogs. And then let's create a function here. We'll just do a private function called make some noise. All right, now with this make some noise function here, we could use generic. So we could say type Z or type animal is going to be anything that has a noise sound. So we could say animal is of type animal sound. And then this allows us to define an input like A is of type animal. And so now anything that has an animal sound trait implementation can be used as input. And this is the generic way of doing things. So what we'll do is just take our A variable and say make sound. Because Rust knows that this A right here is of type animal, and animal is anything that implements animal sound, the Rust compiler knows that we can call the make sound function on the input type. So what we'll do is say make some noise, and we'll pass in our instance of our dog. And remember that our dog implements the animal sound trait so we can pass it in as a generic. So I'm just showing you the generic way of doing things, and then we'll take a look at the dynamic dispatch way of doing things, which is a bit different. So now we want to call that from our main function here. So let's go into our traits test module and call the public run trait test function, which is the only function that we've made public or exportable from this particular module. And so now we'll just do a cargo run. And as you can see, it says dog is barking. So what's happening here is we are constructing a dog, and then we're calling this make some noise function. And because we have animal sound implemented on the dog type here, it works perfectly fine, right? So we can call make sound on a dog. We could also call make sound on an antelope. So if we construct an antelope right here and duplicate this line, do antelope 01, both of those function calls are going to work fine because we're using generics to pass in a trait, and both the dog and the antelope and the bear all implement that trait. Now let's take a look at how to do a similar thing, but we're going to use dynamic dispatch instead of using the generic types, which should hopefully keep our binary size smaller, but it's going to also potentially increase the time it takes to do that additional lookup against the virtual lookup table. So what we're going to do is change our implementation of make some noise here. We're going to remove the generic type right here. And instead, what we're going to do is accept a dynamic pointer to the trait that we want to implement here. So the implementation of our function isn't going to change at all. We can still do a.make sound, and it's still coming from the animal sound trait. So the Rust compiler still knows that that function call make sound is coming from the animal sound trait. So we can still call that function on the a input variable here, but instead of defining it as a generic, we are dynamically dispatching to the trait, and we're looking up from that lookup table the implementation for the function. So now you can see that we're getting a compiler error here saying that it expected a pointer to a trait, but it found a concrete implementation of a dog. So what we can do is when we construct the dog here, we can actually specify that we want a pointer to the underlying trait instead. So what we're going to do is specify that we want a dynamic pointer to the animal sound trait, and then we're going to get a pointer to the dog. So now this dog01 variable doesn't point to a specific instance of a dog. This dog01 variable is now a pointer to the animal sound trait. And remember from the documentation that there's two different things that it points to. Number one, it points to the underlying implementation of the dog that we've constructed right here. And the second is the virtual lookup table that allows us to look up the function implementations. So that's what this pointer, this dynamic pointer, is doing right here. And then we'll do the same thing for the antelope. We can declare the type of antelope as a dynamic pointer to animal sound, and then we'll get a pointer to the antelope struct. And so now we have both of these variables holding the same type. Previously, these variables had a concrete definition of what they were. The first one was a dog implementation. The second one was a antelope implementation. But now, because we're using dynamic dispatch, these variables could actually point to either one. So the dog variable could actually point to an antelope, and the antelope01 variable could actually point to a dog or a bear or anything that implements the animal sound trait. So once again, we can go ahead and pass in these pointers to our function here, and now we get dog is barking and antelope is bleeding. So basically, this is how we implement dynamic dispatch for input arguments to functions. We could do the same thing for eating. So we could do function eat some food. We could take a as an animal input variable, and we could get a dynamic pointer to animal eating as a trait. And then inside of here, we can just say a dot eat food. And of course, this eat food function is known by the Rust compiler because we have the function declaration on the trait, and of course that forces us to implement the function eat food for any types that implement the animal eating trait. So as long as we pass in that animal eating trait, we can go ahead and pass in any animal to that function. So once again, we can say eat some food and pass in our pointer to a dog. In this case, it actually needs to be a pointer to animal eating. So we'll say dynamic dispatch to animal eating trait, and we'll go ahead and create a dog here. And so now if we call eat food, it says dog is eating food. But if we change the underlying type here to antelope, so let's say let antelope 01 equal a pointer to a new antelope instance. And then we call that down here, antelope 01. Now we should be able to get antelope is eating natural desert plants. So again, using traits here, it doesn't really matter which trait we use, as long as we get a pointer to a dynamic trait here, which points to the underlying data structure, then Rust is able to do a lookup of the methods that are implemented for that particular trait, and then perform a runtime evaluation of the memory address of that function implementation. So this is how we do dynamic dispatch for input arguments to functions, but you may remember that we also talked about doing dynamic dispatch as a function return type as well. So instead of passing in an animal, we could actually get an animal back from a function that implements a particular trait. So to do that, we'll do a function down here, and we'll say get animal. All right. Now the return type for this particular function is not going to be a concrete implementation. So we're not going to return a dog. We're not going to return a bear. Of course, those are all options, but if we want to use dynamic dispatch, then we need to return a box of type din and then whatever trait we want. So we could say, all right, I want any kind of animal that can eat. Okay. And so now what we can do is construct an animal inside of this function scope and then return a box pointer to that trait implementation. And then that's going to allow us to return that concrete type back to the caller. And then we can go ahead and call whatever methods we want on that particular return type. So let's say that we construct a bear. So we'll go ahead and just build a new bear. And of course, a bear does implement animal eating. So we can go ahead and return a box from the bear, and that should satisfy the return type right here. So we're going to return a boxed pointer to the animal eating trait for the bear that we constructed, and that should allow us to call the animal eating function on that pointer. So let's do let bear01 equal get animal. And so now we have in bear01 right here, we have a boxed pointer to the animal eating. So now we can do bear01 dot eat food. And of course, that's the only function that's going to be available because we're doing dynamic dispatch here and we are retrieving a animal eating trait reference to the underlying bear. You'll notice that when we do bear01 dot, if we try to do make sound, I think it is that the function name that we had for the animal sound trait? Yeah. So if we try to do bear01 make sound, you can see that we can't actually call make sound because the pointer that was returned from the get animal function was a dispatch to a trait, not to the actual data structure. So we can't call make sound on the bear, but we can call eat food because eat food is the method that's defined by the animal eating trait. So now you can see it says bear is eating some other animal. And of course, we could always change the return trait here to animal sound. And now we can't call bear01.eat food because that's not available on that trait, but we can do bear01.make sound, and that will allow our bear to roar. So that's how we can use a trait as a return type. And what you'll notice is that when we use a trait as a return type, we don't necessarily know as the caller, right? So our caller up here on line number 12 and 13 doesn't necessarily know what type it's going to get back. So what we'll just say is animal01 as the variable name, and then whatever animal we get back. We don't know if it's a dog, we don't know if it's an antelope, we don't know if it's a bear, but whatever animal is returned from the get animal function right here, we're just going to call make sound on it. So the function here, the function implementation can say, all right, well, I'm actually not going to return a bear. Let's just do let animal equal dog. And then we'll change this here to return the animal. So now if we return a dog, it'll say dog is barking. And if we return an antelope, so if we construct an antelope instead of a dog, it still works perfectly fine because Rust is only looking at the trait boundary here. It's not looking at, not really trait boundary, but the trait type that's declared here. And it's calling make sound on whatever animal is returned from the get animal function. So again, this is how we use dynamic dispatch at runtime of our Rust application to do a lookup of the method implementation in memory and run that particular implementation for that type. Now, the other concept that we said we were going to talk about is called supertraits. As you probably noticed in our application right here, we have two different traits that we're dealing with. We have the animal sound and we have animal eating. We could have animal running. We could have a whole bunch of different traits that define various behaviors, right? And we could treat each of those individually. But what if we wanted to just deal with animals more generally? As you saw in this previous example right here, when we return a specific trait, we can only call the functions that are available on that specific trait using dynamic dispatch. I can't call the eat food function on a bear if I return a reference to its trait for animal sound, and vice versa. I can't return animal eating and then call make sound on that trait because each of those traits defines unique behavior. So in order to solve for this, what we could do is say get animal, and instead of returning a specific trait, we could actually return a super trait that implements multiple child traits. So what we're going to do here is simply add in a third trait. Right now we have two traits, animal eating and animal sound. But now what we're going to do is implement a super trait just called more generically just an animal. And for animal here, we're going to do a colon, and then we're going to say animal eating plus animal sound. And we don't need to define any additional methods because the methods themselves are being defined at the individual trait level here. I'm just saying that an animal implements both of these traits right here. So now what we can do with this super trait being defined is go back to our get animal function right here. And remember, we can't call animal.eat food. This is not going to compile because the trait animal sound doesn't declare eat food. But watch what happens if we change this dynamic dispatch return value to just animal, which is the super trait that incorporates both of the animal sound and animal eating traits. Well, we should be able to return an animal that implements both of those traits. So what you're going to see right here is it says the trait bound animal is not satisfied for antelope here. And that is simply because even though we implemented both of these traits here, we still need to at least declare the implementation block for animal. So under the section here for antelope, I'm actually just going to go ahead and group these implementations together so that all of the implementations for antelope are next to each other and all of the dog implementations are next to each other. And let's see, all of the bear implementations should be next to each other as well. And then if we go up to the section where we implement the traits for antelope, we'll just add a third implementation block that's basically empty. The body of it will be empty. So we'll say implement animal for the antelope type. We're going to do the same thing for the dog. So we'll say implement animal for dog. And again, the body can be empty because we're not defining any extra methods for animals. We're just saying that an animal has to implement those two child traits. And then we'll do implement animal for bear with an empty body. All right, so now all three of our animals that we've declared here, and of course we could have 10 or 20 or 100 different types of animals that all have these implementations. Now you'll see that our trait is satisfied here in our get animal function. We're no longer getting an error. So if we do a cargo run, you can see that we are able to call eat food on this animal type. Also, we can do animal 01 dot make sound, and it doesn't matter what type of animal we get back. As long as the type that we return from this get animal function implements the animal trait, we can call both eat food and make sound functions because the animal trait, super trait, requires that both of those child traits are implemented. So if we come back here and change our function, we're just going to make one tiny change. We're just going to return a bear instance instead of a antelope. Now you can see bear is eating some other animal and bear is roaring. If we change the implementation of this function, get animal to dog, and we return a dog instead of a bear, check it out. We can still call eat food and make sound for the dog type. So now that we've got this dynamic dispatch happening for this return type here, and we are using dynamic dispatch for these input functions here, we can now pass around this animal type very generically. We can focus on implementing more animals, right? So all we have to do is implement maybe cats or maybe lions or tigers or whatever other type of animal that has these shared traits. And now we can use these functions to kind of modify or invoke the behaviors of all of these different types of animals. So this is a really nice way to handle the kind of generic implementations. Of course, since I changed the implementations of these functions down here to use animal, we now have to declare the dynamic dispatch type of animal, not the specific child traits of animal. And so now all of those functions are going to work just fine on those generic animal types. So dynamic dispatch is really cool. It helps me to just kind of implement things a little bit more generically when I'm thinking through how am I going to implement my types, how am I going to implement these behaviors on my different types. And it really just opens up a whole window of opportunity to simplify your Rust code and to make things easier to understand as you're maintaining your Rust application. So anyways, I love supertraits. I love dynamic dispatch. I love generics as well, because it really is up to you as a developer if you want to sacrifice a little bit of runtime cost for a little bit of compile time or vice versa. It's really up to you to determine which route you want to go, but feel free to use generics or feel free to use dynamic dispatch now that you have the understanding of how both of them work. All right, so that's everything that I had for this video. Again, if you learned something new, please leave a like on the video. Please leave a comment down below. Subscribe to the channel, as I'm an independent content creator and I'm trying to grow this community. And make sure you hit that bell icon next to the subscribe button on this video to make sure that you get notifications anytime that a new video is released. Thanks again for watching, and we'll see you in the next video. Take care.